So we spent a lot of time last time drawing chair conformations of plain, normal cyclohexane. But this time, we're not going to draw cyclohexane. We're going to put stuff on our cyclohexane, and we'll start out with methyl cyclohexane. So I'm going to draw my two chair templates. Whew. They look better than the last ones, sort of. And I'm going to stick a methyl on here. There's no reference point as far as there's no other group to compare to. So I'm going to stick a methyl right here because I want to. I didn't mention this previously, but these chair structures, the very specific, like the reason we took so long, the positions are very specific for which carbon you're on and which conformation you're in. If it's up on this carbon, up on this carbon, in this conformation, has to be axial. This is that same carbon after a chair flip. The methyl will stay on that same carbon, but up on that carbon has to be equatorial. Has to be. I paused for a second to straighten out my bond angle over here because it was a hot mess. It looks much better now. So on the leftmost example, I would call that methyl up and axial. And the right conformation, I would call that methyl up and equatorial. Cool beans. Now, all we got to do is put this thing in a Newman so that we can talk about the stability of it. Just like before, I'm going to choose to look down this bond and that bond of my Newman simultaneously. Remember, this is the front. I realize that's not very legible. And the back. So I'm going to look at this leftmost example and put it in a Newman. On this carbon, we have an equatorial hydrogen up and axial hydrogen down. So I'm going to make my leftmost Newman carbon match that, and then it's just fill in the rest of the Newman, knowing that all chairs are staggered. It's real quick to fill in the rest. I didn't quite save myself enough space here, but this methyl should be on the back carbon of my Newman, on the right carbon of my Newman, pointed straight up in the air. So that is my methyl in my Newman, and everything else is hydrogen. We previously drew this guy and this guy as a CH2. You can draw those as a CH2. If you check out textbook things, they often have a single H just pointed straight up like that, or a single H pointed straight down like that. Those are the axial hydrogens that they're trying to specify, but I often leave off those middle hydrogens. And let's do a chair flip. I need 2 circles for my Newmans. I'm going to move this carbon down, so that makes my orange central carbon point down. And I'm going to make this carbon move up, so that makes my purple up. So this is the template of my molecule, the template of what my chair looks like, my chair flip. If I trace that methyl, this methyl, as that back purple carbon goes up, this methyl will shift to be over there, that direction. I fill in the rest of my hydrogens. I will keep these color-coded here that those 2 hydrogens on the front carbon are black because they were before, but really there's nothing significant about them. I'm just wanting to be consistent. So check it out. This methyl, axial, straight up, in my Newman, that's straight up. That position is an axial position. In my chair flip, up and equatorial. Oh look, it's still up, but now it's in an equatorial spot. We did a good job drawing these Newmans. Okay, let's talk about stability. Why is one chair more stable than the other? Because I'm telling you, one chair is more stable than the other. The reason one chair is more stable than the other is due to what we talked about in the Newman video, gauche interactions. What? Where the heck are these gauches? So this carbon is gauche to that carbon. Remember, gauche means big things next to big things. These two carbons are gauche. In fact, they're gauche in both Newman projections. But there's an extra gauche interaction between this ring carbon and this methyl when that methyl is axial. When the methyl is equatorial, not so much. When the methyl is equatorial, he's next door to two hydrogens, and that's fine. So anytime something is axial, there's an extra gauche interaction with the ring carbons. So it's always lower energy for substituents to be equatorial than axial. What does that really mean to us, or why do we care? It means that a molecule spends more time looking like this or in this chair conformation than it does in that chair conformation. These are equilibrium, remember. It flips back and forth constantly, but it spends more time in the more stable conformer than it does in the less stable conformer. So this slide is wanting us to draw the Newman projections for axial, but we squeezed it all on the last slide because we're good like that, I suppose. When a methyl is axial, it's said to have 1,3 diaxial interactions. That means the methyl interacts with the other groups that are axial pointed the same direction, and that's not favorable. Remember, electrons don't like to be near each other, and when they're axial, they're closer together than they would prefer to be. That's not great. So that was simple methyl cyclohexane. What if we put two groups on a cyclohexane, or even more than two groups on a cyclohexane? How does that affect things? First, a definition. What are constitutional isomers? Constitutional isomers have the same molecular formula but different connectivity. If you were to name this molecule, you would call it a 1,2-dimethyl cyclopentane. You would call this one a 1,3-dimethyl cyclopentane. Both of them fit the same molecular formula, C7H, let's see how fast I can count, 2, 4, 6, 8, 10, 12, 14. Both of them fit the formula C7H14, but they are absolutely 100% different molecules. Constitutional isomers, same formula, different connectivity. Same formula, definitely different molecules. Another definition. What are stereoisomers? Stereoisomers have the exact same connectivity as far as you would name them the same compound, sort of, based on what we know so far. Let me say that. 1,2-dimethyl cyclobutane, well, that's this. 1,2-dimethyl cyclobutane, that's this. But these are called cis and trans isomers. They're called stereoisomers. Stereoisomers have the same connectivity, but their atoms are arranged differently in space. So this methyl is coming out toward me. So is that one. But this one is going away, and that one is not. What does this have to do with chair structures? Cyclocompounds, like we said in the previous video, cyclocompounds cannot rotate. They can twist and tweak and flip and flop, but they cannot rotate. So you can never turn cis, no matter your rotational stuff, you can never turn cis into trans. You would have to break bonds in order to turn cis into trans. You can never turn cis into trans with rotation. So anytime you have restricted rotation, you may have cis-trans isomers, like in cyclocompounds. Also in alkenes, but we're not there yet. So with the definitions out of the way, on to more cyclohexanes. This is a di-substituted cyclohexane. It's specifically called trans 1,2-dimethyl cyclohexane because trans means on opposite sides. One pointed up, one pointed down. This guy's up, that guy's down. We've been given a pretty picture of trans 1,2-dimethyl cyclohexane. This over here is called a Haworth projection. Those are much more common in biochemistry than organic chemistry, but I may as well tell you that's what that is. There's ups, there's downs, but it does not show correct bond angle. That's why organic chemists don't love it as much. So here's our pretty chair conformation, but let's see how we would actually walk through a problem like this if we were told, draw this molecule in its two chair conformations and decide which is most stable. Let's do that. So I'm going to start out by drawing my chairs, obviously. You don't have to draw this one first, but you will learn that you're probably better at drawing one chair conformation than the other. And that's the one I always start out with because, I don't know. So if I look at this chair, I have to choose a perspective to look at the chair from in order to see how it should be drawn three-dimensionally. What? Yeah. Remember when we drew all those models that had a red carbon, a blue carbon, something coming toward your face, something going behind? Yeah. Depending on the perspective that you choose to look at this molecule from, different things will be on different carbons, and you want to make sure that you properly map this carbon stuff to this carbon stuff. So let's give it a shot. If we stick with our similar stuff as yesterday, if this is where my eyeball is, that means that this carbon is my red carbon, that's my leftmost carbon, and this one directly across the ring from it is my blue carbon. So we could put the same dots on here. Do you have to do it this way? No, but it's a little bit difficult to just lecture to a computer and expect the people on the other end to understand this well. So here we are. When I'm choosing to look from this green eyeball over here, the red carbon is on my left and the blue carbon is on my right, based on the perspective I have chosen. I'm turning my head that direction. This bond is coming toward my face. Red is on my left, blue is on my right. Okay, so red carbon has a methyl on it, and based on the perspective I've chosen, that methyl is pointed up. So then you have to know that up on that very carbon, what's the template look like? Where is the methyl if it's up on that carbon? Up on that carbon is axial. I almost made an H. It's a methyl. On the red carbon, up is axial because of, I said that poorly. On the red carbon, the way I have mapped my two molecules, on the red carbon, when a methyl is up, then on this molecule, it's going to mean axial. Okay, let's try another one. If I say this carbon here has a methyl, be sure that you understand that green dot carbon and that green dot carbon are the same thing. Remember, the bottom line of a chair is coming toward your face. So my methyl on that green carbon is pointed down, and pointed down on the green carbon chair structure over here means axial as well. So it's all about the templates of my chair structures. It's not just up means axial, down means equatorial. It depends on how you map your molecules together. Hopefully that makes some good sense to y'all. I don't know how else to explain it, but maybe I'll get some feedback later. Okay, so if I do a chair flip, this methyl, describe it in 2 words, it's up, it's axial. When you do a chair flip, axial becomes equatorial, but what's up stays up. So this is my red carbon that I've colored over and now looks purple. That methyl should be up and equatorial on that carbon. This other methyl should be on this carbon, and if I described it in 2 words, I would describe it as down and axial. So it must be down and equatorial in my chair flip. Yeah? Which chair structure is more stable? Obviously, the one where everybody is equatorial, because everybody gets their own space when they're equatorial. This axial version will have extra gauche interactions, an extra gauche because of this purple, and extra gauche because of this green. There are fewer gauches in this one, which leads it to be more stable. You could draw it in Newman's to prove that with gauches, right? 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 Right. That was not so bad. I think I can do another one. How about cis, 1,2-dimethylcyclohexane? First, define cis. It means on the same side, either both up or both down on a chair structure like this. Note, cis and trans can only designate two things on a ring. If you have more than two things, you got to do something besides cis and trans, and we don't know what that is yet. But same as before, let's pretend we were given the question, draw this thing in its two chair conformations, tell which is more stable and why. Here's my two chair templates to get started. I'm going to choose the same perspective as before, where I'm looking over here. This is my left-hand side, this is my right-hand side, and let's see if I can map things without quite so many colors. So on the leftmost carbon, I have a methyl group. A methyl that I would say is pointed up because it's pointed out of the plane of paper, and that's where I put my head. So up on my leftmost carbon, using this template, up on my leftmost carbon means axial. Okay, going on around, if I look at this carbon, that's my neighbor here. Up on that carbon means equatorial. Okay. Chair flip. Hopefully in your head you're processing whether my groups should be up or down or axial or equatorial. But there it is. That's my product. Our question was, which one, if either, is more stable and why? Both of these have one axial and one equatorial substituent, so that means they are equally stable. What does it mean to be equally stable? They spend equal amounts of time in both chair conformations. If we flip backwards real quick, we said this green circled one is more stable than the other. What that really means is equilibrium favors the green circled one, and it spends more time in the green circled conformation than it does the other conformation. That's what it means for a chair conformation to be more stable. So since we drew 1,2-dimethylcyclohexane, the cis isomer and the trans isomer, we can actually also compare cis to trans as far as stability. In the cis, both conformations had one axial, one equatorial. In the trans, we had an axial-axial and an equatorial-equatorial. This isomer, this conformation, is the most stable of all four chairs that we just drew, which leads us to say that the trans isomer is more stable than the cis for 1,2-dimethylcyclohexane. Please note, do not take my words to say trans is more stable than cis and that the universal rule. It's not. So what are the universal rules? The most stable conformation has the biggest stuff equatorial. We had methyls on all of our stuff just now, but what if it were ethyls or propyls or et cetera, et cetera? The biggest stuff, the biggest substituents equatorial is the best. The most stable stereoisomer, that's the last thing we just did, cis versus trans, is the one that has the biggest stuff equatorial. The one that has the most things equatorial if you have more than two. I think we can handle a little bit more. Maybe not a lot, but a little bit. What about cis, 1-tert-butyl, 2-methyl-cyclohexane? First thing we need to do is establish what it looks like in a planar structure, in a perspective drawing. I'm going to call this carbon number 1 just because I can, and I'm going to put a tert-butyl on it. And I'm going to put a methyl on this carbon just because I can, and call that carbon number 2. If it's cis means same side, both up, both down. So I'm going to turn that into a wedge coming out toward me, and that one has to match. Same thing. Because it's tough enough to view things in 3 dimensions, period, I'm going to choose my same perspective. Here's my left, here's my right. Let's draw some chair templates. If I make this methyl purple, that's on my rightmost carbon from my new perspective. So that means this carbon. that methyl is pointed up because it's coming out of the plane of the paper in planar, and then when I change my perspective, it's coming up. Up on the purple carbon down here means equatorial. There. Okay. Cool beans. What about this big honkin' tert-butyl? Tert-butyl back here on this carbon also pointed up because cis means same side, pointed the same direction. So up on that carbon is axial. It's the carbon of the tert-butyl that's axial. And then the rest of the butyl is just branched off of there like a normal branched thing. Okay, cool. Green carbon maps to that spot. That's the same carbon. Tert-butyl is up and axial, flips to up and equatorial. Okay? Purple. Methyl is up and equatorial, flips to up and axial on that purple carbon. So which isomer is more stable? If we're considering equilibrium, which conformation does this molecule spend more time in? This one. Equilibrium favors the right-hand molecule because tert-butyl is giant, and tert-butyl being axial is real bad news. Tert-butyl is too big to be axial. It's too unstable to be axial. Those 1,3 diaxials, ooh, bad news when tert-butyl is axial. So it spends the majority, almost all of its time in this conformation because that axial tert-butyl is bad news. If we just looked not about size, we've got one axial, one equatorial in both, that's not good enough. We have to consider the inequality of tert-butyl and methyl as far as size goes. Okay. I think I've got one more in me. Well, let's try trans, 1-tert-butyl, 2-methyl cyclohexane. We'll draw it in the same orientation as before, because if you didn't notice, it's the same molecule as before, 1-tert-butyl, 2-methyl, except this time it's trans. So if I put my tert-butyl up, I'll have to put my methyl down. If my tert-butyl is wedged, my methyl has to be dashed. Same perspective, just so we can avoid any confusion. Purple methyl is on my rightmost carbon. That's this one. That methyl is pointed down from my current perspective. Down on this carbon is axial. If I do a chair flip, down on this carbon is equatorial. How about the tert-butyl, the green one? It's on that carbon, and it's up. Up on that carbon is axial. Up on that very same carbon in a chair flip, equatorial. Which conformation is more stable? This one. It spends more time in that right conformation than the left conformation. It spends way more time, in fact. If we were comparing cis versus trans of these two molecules, just like the first example we worked, cis has 2 axial equatorial chairs. Trans has an axial chair. That's this one. And an equatorial chair. That's this one. Because trans has this equatorial, that makes trans the more stable stereoisomer of 1-tert-butyl, 2-methyl cyclohexane. Good enough? Good enough. Here are 2 examples that you should try. We should probably discuss them together the next time we get together. That's all for now.